The last part of our chapter, we will talk about what gets conserved in different types of collisions. We're also going to talk about work due to friction and then conclude with some example problems. So let's get started. I hope you remember there are two types of collisions. Elastic collisions would be when objects typically bounce off of each other. So they will stay separate objects after they've collided. And then inelastic collisions were the ones where objects tended to stick together. So they became one big tangled mass. Both of these collisions conserve both momentum and energy, but specifically with the kinetic energy side, that's where they're going to differ. Elastic collisions will conserve both momentum and kinetic energy. For an inelastic collision, because you have those objects becoming coupled and tangled together, they're only going to conserve momentum and they're losing some of that kinetic energy. It's turning into heat. So heat is still a type of energy, but it's changing from kinetic to heat. So we're losing some of that kinetic energy. And the reason that happens is because of work due to friction, which is our next section. So hopefully you remember previously we talked about the work done on a system being equal to the change in the energy of the system. So if we have not all of our potential energy turning into kinetic or some of our kinetic turning into heat, then some of that energy is lost due to work done against friction. And to actually calculate that work, we are going to simply subtract potential energy minus kinetic energy. Now, for us, you're not going to have to calculate how much heat was lost for anything. We're only going to look at the difference between the potential and the kinetic. So there should always be more potential energy, and you subtract the kinetic energy, and that'll tell us how much work was done by friction. And then don't forget, the units are going to be joules. So I've got a few example problems for you. I'll get you started. This first one, we're going to start with a 15 kilogram rock. It's sitting on the edge of a 90-meter cliff, and then we've got a few questions about it. So let's draw a picture and kind of get an idea of what's going on. Okay, so there's our cliff, and we have this big rock up here. We know that the mass of the rock is 15 kilograms, and we know that the height that the rock is, its vertical displacement is 90 meters. And we were not told a specific reference point, so we are assuming that the ground is the reference point and our vertical displacement would be a positive 90 meters. So first we're asked to find the potential energy. This one should be a simple one for you. We're simply going to look at the potential energy formula, which would be mass times gravity times height. So let's plug those numbers in. And I'm going to switch screens so we can get our final answer. So remember, we were looking for potential energy. We simply substituted in the values that we know for mass, gravity, and the vertical displacement or the height, and you should come up with a value of about 13,230 joules. Next, we are told that the rock falls from the cliff, and we want to know the kinetic energy just before it strikes the ground. So remember our picture, we had a vertical displacement, so it started out with all potential energy, and then as the rock's going to fall, that potential energy will decrease because there's a decrease in vertical displacement, and hopefully you remember that it gets faster as it falls, which means our kinetic energy is going to increase. And that moment just before it hits the ground, we're going to assume that there's no vertical height there, so it's lost all of its potential energy and turned into all kinetic energy. So mathematically, let me show you how that works. We're going to look at the conservation of energy. Before the rock falls, so while it's still on the cliff, we've got potential plus kinetic, and then after it's fallen, right before it hits the ground, we're going to look at the final values for the potential and the kinetic. So while it's still on top of the cliff, it was not moving. It had all potential energy and zero kinetic energy because it had no velocity. And then after it fell, it reached that reference point. So we say that it has a height of 0 and it's the fastest point as it's hitting the ground. It's moving, so it still has kinetic energy. And we simply reduce that down, and that gives us a final kinetic energy of 13,230 joules. Notice that these numbers are the same as long as there's no friction. So I made you a little note. All of the potential energy that we started with will change into all kinetic energy only if there is no friction. And there was no friction in this problem, so we can simply have the same magnitude for both potential and kinetic energy. Now, the last part of the question wants to know with what speed does the rock strike the ground. You could use kinematics. If you remember that from last semester, you're welcome to use your kinematic equations and find that final speed. However, since we have kinetic energy, I'm going to use that version. So I'm going to start with my kinetic energy of 1/2 mv squared. I'm going to substitute those values. My kinetic energy was 13,230 joules. The 1/2 was in the formula, the mass was 15 kilograms, and I'm looking for that speed. So I reduce down a little bit, and then I can divide both sides by 7.5. Don't forget, when you get to this point, you do want to take the square root of both sides, and that leaves us with a speed of 42 meters per second. For our second question, we've got a 25-gram Hot Wheels car, so let's write our mass. I hope you remember how many kilograms that would be. So remember, we're going to divide by 1,000. We have a velocity of 4.2 meters per second, and then this track is suddenly going to turn upward, and we want to know how high up that track the car can travel. So we are looking for a vertical displacement. We're going to look for that height. So first ask yourself, is there any friction mentioned anywhere in the problem? In this case, no, there's no friction. And what that means for us is that we can have the same number of potential energy that will plug in for kinetic energy. So I made you a note, there's no friction. This means that the potential and kinetic energy are going to have the same magnitude or the same size. So typically, when we look for the height of something, you would probably go automatically to potential energy as mgh. However, we don't know the height, nor do we know the potential energy. But we do have enough information where we can find the kinetic energy. And that would be 1/2 mv squared. And remember, because there was no friction, I can take whatever number I get for my kinetic energy and plug that in for my potential energy because of that conservation law. So let's do that on the next page. So let's go ahead and plug in and calculate what the kinetic energy would be. And I came up with 0.2205 joules. And because of our conservation law, we know that all of the kinetic energy will change into all potential energy. So I'm going to write that out for you. So I walked you through all the steps. At the beginning, there was no potential energy because it was on the ground, and it had all kinetic energy traveling horizontally along that track. Finally, when it went up the ramp, it would change into all potential energy, and at the top of that path, at its highest point on the ramp, it would not have any kinetic energy. So this shows us our value that we can plug in for potential energy and use that to find our height. So this is where we left off. Let's plug our numbers in. So we plugged in for the potential energy, the mass, gravity, and now we're going to solve for the height. So try it out and see if you get the right answer. You should have gotten a height of about 0.9 meters. So that's about 9 centimeters up the ramp that car was able to travel. Our last problem will ask you specifically how much work is done by friction, so we know that the potential and the kinetic energy values are not going to be the same as each other. So in this case, we have a little kid, Logan, about 32 kilograms. He's going to climb up a 4.2 meter ladder of a slide, and then by the time he reaches the bottom of the slide, we are asked to find how much work was done by friction if he reaches a velocity of 3.7 meters per second. So let's identify our values that are given in the problem. We know what the mass is, we know what the height is, and we know the velocity. When we were asked to find how much work was done by friction on Logan, hopefully you remember that to find the work due to friction, you simply subtract potential energy minus kinetic energy. I'm sure that you know how to calculate both of those, so I'm going to let you pause the video. I would like for you to calculate the potential energy, the kinetic energy, and then find the work due to friction. So go ahead and pause and then come back and check your work. Good. I hope you found that the potential energy was about 1317 joules, a little over 1300. The kinetic energy should have been about 219 joules. So you can see that he actually did lose a lot of energy, somewhere in the neighborhood of 1100 joules. So remember, if you have an example problem where there's no friction, all of your potential will turn into all kinetic. However, if there is work done by friction, then you would simply find the potential energy, find the kinetic energy, and then subtract them to get the work for your final answer. I hope this was simple enough for you. You are going to have some word problems similar to these on the test. And if you do have any question or if some of this didn't make sense, make sure that you come in and ask me for help. There are also some really good study guide problems at the end of your notes that can help you prepare for your test. Thank you for listening, and that concludes our chapter on work and energy.